Hello and welcome. Today we're going to talk about experience of learning mathematics. But before we begin, I would like to share my vision about this channel, and I would very much appreciate some viewer feedbacks on that. So I'm planning to, first of all, upload more consistently, and second, try to balance two types of content. The first one is actual mathematics, that is more formal and more detailed and more technical. And the other type is more casual, for example, today's format. It may be opinions about math or science related topics in general, and also book reviews, which seem to be quite popular. So, let me know about that. Let me know in the comment how you feel about these types of content. Today's topic is about motivations or the lack thereof in mathematics courses. Now, I'm not talking about psychological motivation. I came across this Reddit post. I apologize for the wall of text. Instead of spending time teaching conic sections, we should teach more statistics. The post says, speaking mainly from my experience in the US, but this could be applicable to other regions as well. Status quo. High school math courses spend a considerable amount of time going over conic sections and their equations. Meanwhile, statistics is only taught to a cursory level. Students learn about mean, median, mode, and plus basic probability and combinatorics. My problem, to me this makes no sense. What is the point of spending so much time learning about ellipses and hyperbolas and how to turn their equations into standard form and such? In STEM, they're useful to know about, but very niche compared to statistics. Outside STEM, they're near useless to understand on a mathematical level, whereas statistics is very helpful for everyday life and non-STEM fields of study. Instead of having 2 to 3 months focused on conic sections, revise the curriculum to spend that time on statistics and statistical reasoning. Before coming back to the post, I would like to share my personal experience learning linear algebra. When I took my first course on linear algebra, it's very similar to the content of this book, so let's take a look. The course I took on linear algebra focuses on proofs and algorithms. There's very little motivation of why we do certain things, but it was a solid course in that regard. We talk about vector spaces, which generalizes the notion of vectors learned in high school, and within it, we learn how to solve system of linear equations, namely by Gaussian elimination, which is the main workhorse for computation in elementary linear algebra. And then we learn about linear transformation, kernel and image, rank nullity theorem, that kind of stuff. The determinant function, I had a huge issue with determinant because it was completely unmotivated. Here in this book, it actually put the determinant as area at the start, so that's a nice thing. So it's quite common for first courses on linear algebra to introduce determinant in the form of a big formula, which is quite ugly, that involves either permutations or a recursion, that's the Laplace expansion. And then you just do a bunch of calculations, prove this property, and at the end it turns out, oh, it's actually the area. So this is a nicer approach in my opinion. And then we learn about eigenvectors, diagonalization, and spectral theorems. So they turns out to be massively important topics all across mathematics and sciences in general. But learning those things as a first year student, we had absolutely no idea why they were introduced. I was just following the definitions and formulas to perform routine computations and also some proofs. But again, just had very little idea of why we're learning this stuff. Chapter 5 is on complex numbers and complex vector spaces. Chapter 6 is on Jordan canonical form. The last chapter is about differential equations and linear differential equations in particular. And at the end, we have 2 appendices, one about basic logic and set theory, and the other one about mathematical induction. So these are a crash course on how to write proofs, because this book is intended for first-year students, and some students may have little experience with proof writing prior to taking this course. Just to take a quick look through the actual pages, and I would regard, in my current point of view, a very solid book. The definitions are careful and the proofs are complete. Numerous exercises mixed with computations and proofs. So from that regard, as a solid linear algebra, qualinear algebra course, this is an amazing textbook. But if you're someone whose primary interest is not in mathematics per se, it might feel a little bit dry. There's very little actual applications beyond mathematics, right? So I'm not talking about application within the mathematics. For example, this section called the applications of the dimension theorem, which is also called the rank nullity theorem. The format seems really no different from any other sections, consist of statements and their proofs. Once again, if you're not a math major, you might struggle to see why these are actually applications. So based on my personal experience as well as that Reddit post, for one reason or another, a lot of math courses do not discuss the application and motivation of the subject matter. I would love to know your experience and your thoughts in the comment section. So coming back to the post, I would argue against replacing conic sections in the curriculum by more statistics. I'll explain my reasoning, and also we'll see some concrete examples about the application of ellipses and hyperbolas in statistics, explained at a higher level. Statistical reasoning and mathematical reasoning are actually quite different things. Much like the disciplines such as physics and economics that makes use of mathematics, statistics is not a branch of mathematics. The standard of truth, I'm not saying it's higher or lower, it's just different. To establish or dispel an assertion in mathematics, we need proof or counterexample. In statistics, on the other hand, we may establish a pattern using charts. And to quantify the pattern, we use statistical models, and the models are evaluated using confidence intervals and p-values. Of course, statistics and mathematics, they do overlap. It's the field called mathematical statistics. Mathematical statistics uses probability theory to study the properties of statistical methods, and in particular, whether a method is optimal in some sense. Let's look at some of the applications of conic sections in statistics. Let's first look at ellipses. Suppose we're given a set of paired observations, such as the height and the weight for a group of people. Such data can be visualized by a scatter plot and are often clustered around some center. So we observed a pattern in our plot. A popular model for such pattern is the bivariate normal distribution. We can think of it as a two-dimensional analog of the familiar bell curve in one dimension. This idea can be elaborated by drawing the contours of the bivariate normal distributions. Roughly speaking, points on the same contour are equally likely. All these contours are ellipses. They have the same center, the same orientation, just different scale. Quite often, we wish to find the directions on the plane along which the data has the greatest or the lowest variability. This amounts to finding the major and minor axes of the ellipses. This technique is known as the principal component analysis, or PCA. In algebraic terms, PCA is the problem of finding a transformation that converts the ellipse equations into standard forms. In practice, the ellipses are in general oblique, meaning their axes do not align with the coordinate axes. So high school algebra isn't quite up for the task, and we would need linear algebra to perform PCA. It is in fact an eigenvalue and eigenvector problem. According to Wikipedia, it is applied to the study of intelligence, market research and quantitative finance, and neuroscience. The ideas of principal component analysis dates back to 1886 and is due to Sir Francis Galton in his research on human genetics. This is an original diagram from that work. It displays the relationship of the heights of adult children versus the average height of parents. The region bounded by the ellipse is where the majority of data points are. The two axes of the ellipse, namely the principal components in today's term, are plotted as well. Moving on to the application of hyperbolas in statistics. This example is about confidence bands in linear regression. Suppose that, once again, we have a set of pairs of observations, denoted as x1, y1, x2, y2, and so on. The linear regression model assumes that, given that x is fixed, the expected value of y, i.e. the conditional expectation, is a linear function of x. This linear relationship can then be estimated from the data and is called the least square line. X is considered given, therefore fixed, and y is a random variable. So here's the question. we wish to find a 95% confidence region for the true mean responses at every x value given in the data. For example, the true mean response when x equals to x1 is a plus b times x1, assuming that a and b are the true coefficients. So the problem is to find a 95% confidence region for all the true means. In a previous video, I explained the meaning of confidence regions in detail. So if you're interested, go check out that video. And here is an answer to that question. The confidence region is a band whose boundaries are two hyperbolas, with one hyperbola above the least square line, and the other hyperbola is below the least square line. The vertical gap between the two hyperbola are narrower when x is near the average of x, and it gets wider when x is far away from the average of x on both sides. We emphasize that this confidence band is for estimating all the true means simultaneously. And in fact, this is the first method in the history of statistics that performs simultaneous estimation. This confidence band in linear regression first appeared in 1929 due to these two economists and statisticians named Holbrook Working and Harold Hotelling. They used the method that they invented to analyze trend in potato production. In this chart, the zigzag line is the actual observation. The straight line is the estimated linear regression model, the least square line. The shaded region is a 95% confidence band for the true mean response at each year. The upper and lower boundaries of the confidence band are hyperbolas. Thank you very much for making it all the way to the end. You can find more information about principal component analysis and the working Hotelling confidence band in their Wikipedia pages, links in the video description. Thank you very much for watching, and I'll see you next time. Bye.